Hello everyone, my name is Arnav Nigam and I am a student of grade 9 from India. I have prepared a project on the Taylor Maclaurin series and its applications for the WMI Mini-Mat Creative Competition. So, a little bit about the history. The Greek philosopher Zeno had considered the problem of summing an infinite series to achieve a finite result, but he had rejected it as an impossibility, which led to the famous Zeno's paradox. Aristotle and Archimedes worked on this method, but later on in 1715, Brooke-Taylor found a general method to construct infinite series for all functions which had an expansion, and a special case of this series was published by Colin Maclaurin in the 18th century. This is a definition of a Taylor series, which is a real or complex valued function that is infinitely differentiable at a real or complex number a, which is the power series mentioned. Striking feature of the series is that as we go on increasing the number of terms in the expansion, we keep on getting a more accurate graph of the function. The Maclaurin series is a special case of the Taylor series, which is obtained by setting the value of a as 0 in the Taylor series. So as you can see, when we put the value of a as 0 in the Taylor series, we achieve the Maclaurin series. So we can say that the Maclaurin series is the Taylor series evaluated or centered at 0. An overview of the Taylor-Maclaurin series applications. The Taylor series expansion is an awesome concept, not only in the world of mathematics, but also in optimization theory, function approximations, and machine learning. It is widely applied in numerical computations when estimates of a function's values at different points are required. Taylor series is an idea which is used in computer science, calculus, chemistry, physics, and other branches of higher mathematics as well. So let us talk about some applications of the Taylor-Maclaurin series. So the mathematical uses include the following. Firstly, evaluating limits involving functions with known Taylor-Maclaurin expansions like the given function. For this function, we can use the approximations of ln1 plus x, which is given by the Taylor series expansion of this form. Using this expansion in just up to 2 terms, we obtain quite an accurate result of -1. Here, I have also drawn the graph of this function. So, and we can fairly see that as we go on extending the graph till x equals -1, we obtain the limit of y. So, moving on, the mathematical uses further can be used to calculate the exact value of pi, and the value of pi is given by the following generating function of the Taylor series. This can also be referred to as the continued fraction of this form. So as we all know, pi is widely used in most calculations for building and constructions in quantum physics, communications, music theory, medical procedures, air travel, and space flights. Moving on, other applications include the proof of the Euler's formula, which is considered to be one of the most beautiful equations in mathematics. The proof of the Euler's formula uses the Taylor-Maclaurin expansions of e to the x, cos x, and sin x. Euler's formula is commonly used in projectile motion, including drag, and it is commonly used in complex number theory and calculating logarithms of complex functions. Moving on, we can evaluate integrals that cannot be computed using known methods, like the given integral, which is the integral of sine t over t dt from 0 to x. We can use the expansion of sine of x, and we can obtain the value of this integral as mentioned. We can also define Taylor polynomials using the Taylor series. So the nth Taylor polynomial is like the Taylor expansion till the n terms. Understanding the growth of functions solving differential equations are some of the other functions of the Taylor-Maclaurin series. Taylor expansions are widely used in mechanical and electrical engineering too. Other real-life applications include transistors, when we can measure linearity as well as non-linearity of transistors. It can also be used to approximate transcendental functions, and it has a lot of application in this theory of special relativity, because in the approximation of Lorentz factor, we require the Taylor-Maclaurin approximations. So you can see on the screen that the Lorentz factor gamma is written as 1 over root of 1 minus v squared over c squared. That is actually found out after approximating using the Taylor series. The approximations of sine theta for smaller angles, where theta is in radians, we can approximate it as sine theta is approximately equal to theta. In economics, we can measure risk aversion or the connection of expected utility functions and mean variance analysis in finance. It is also used as a starting point for numerical differentiation in simulation models. So this was all about the real life applications of Taylor Maclaurin series and a little bit introduction about them. Thank you so much